This is a follow-up to my last video where I calculated the gradient with respect to the initial condition and then used gradient descent to modify it. One thing I forgot to mention was that in the backwards in time adjoint equation, we need to calculate del f by del y. And in our case, f is a very simple function. It's equal to minus cy, which gives the value of the right-hand side to be equal to a times c. And we just plugged in that value directly in here. At this step, dA by dt was defined to be a times c. This is a bit of cheating because we just obtained the analytical value of this expression del f by del y and plugged it in directly into this equation. Practically, you won't have access to these analytically closed form solutions of gradients, and you'll need to use something like a vector Jacobian product, which is mentioned at the end of this article. But anyway, this is something I forgot to mention. And the second thing is, for all the examples in this article, we will be using closed form solutions. We won't be obtaining them with VJP, and the reason is because I want to highlight the main algorithm which defines the adjoint equation and calculates the gradients with respect to inputs or parameters using that equation. The highlight is not calculation of these gradients. So just a note, we'll be using these values which we obtain manually and focusing only on the adjoint equation part. With that said, let's move on to our second case where we want to optimize the parameter of an ODE. In our case, that parameter happens to be the value c. Just like the previous case, we have a target point here which we want to reach using our ODE trajectory. And let me draw that trajectory first. Run the forward ODE. And as you can see here, there's a gap between the endpoint and this target point. In this case, our initial condition is going to be fixed, but what we'll be modifying is the parameter, which happens to be c in our case. The adjoint equation looks very similar to the adjoint equation for initial condition. Here we have a new variable AP, which is the derivative of loss with respect to the parameter p. And it looks quite similar to the adjoint equation for initial condition. Here we have dAp by dt is equal to minus a del f by del p. Note that a here is the derivative of the loss with respect to y. And in this case, we take the partial derivative of f with respect to p. And this makes sense because if you look at the shapes of these Jacobians, it makes sense because the shape of A is going to be something like 1 times the dimension of y, and del f by del p is going to be something like the dimension of y times the dimension of parameter p. And their matrix product has a shape of 1 times the dimension of p. So the shape checks out, and in this case I won't go through the derivation. It's a bit more complicated than the previous case, but I'll just go over the iterations quickly. In this case, f is still the same equation, it's minus cy, but since we are calculating the partial derivative with respect to c, del f by del c is equal to y, and the adjoint equation that we obtain is dAp by dt equals ay, and this is the equation that we want to solve. Now the interesting thing here is we need two different things from this equation. We need the value of y at every point t, and at the same time we need the value a at every point t. We can obtain the value y using this forward trajectory, but we don't have a trajectory for a yet. So in order to be able to obtain a at any given point in time t, we first need to draw a backwards in time trajectory for a, and once we have that, we'll be using these two trajectories to obtain these two values, and then we will run a third trajectory which is also going to be backwards in time to obtain the gradient with respect to c. So let's see what that looks like. So we run the first backward equation here, and this is the equation for a, which is the derivative of loss with respect to y, and then we run another backwards in time ODE, which uses values of y from this one, from this trajectory, and the values for a from this trajectory, and we obtain this trajectory here. And the point we need is the point at the end time, which in this case happens to be this one. So let me highlight this point. It's grad PD 0. This is going to be the gradient with respect to c. As you can see here, it's negative, and after gradient descent, the value of c is going to increase, which makes sense. Anyway, we perform the gradient descent step and we update the text, and in this case, the value of c increased a little bit. And as you can see here, I haven't drawn the trajectory with this updated c yet, but as you'll see shortly, this trajectory will move a little bit closer to our target point. So just to reiterate what we just did, we ran a forward trajectory of the given ODE, then we ran a backward trajectory to obtain the values of a, and then we ran the third trajectory, which is the second backward trajectory, which uses values of a from this one, from this trajectory, and the values of y from this trajectory. I think in the actual paper they did not run these three equations. This is just done for the sake of clear exposition. I think in that case what they were doing was they were calculating the values of y and a on the go at the same time. That's a lot more efficient, and I think it's also a bit more accurate. But anyway, for the sake of this example, I think it works pretty well. It's a very simple example, and we can also afford to try something different to get a better understanding of how these things work. So anyway, let's run this for a few more iterations. So we run this again. This is our forward trajectory, first backward trajectory and second backward trajectory. And as you can see here, in the second iteration, the endpoint is much closer to the target point compared to the first trajectory. And now we update the text. Our c has increased to 0.67, and we do the same thing all over again. And once more. So in just 4 iterations, we have gotten pretty close to a target point by modifying our parameter c. That covers the second case, and the third case is optimizing the start time t. So in the third case, we'll keep the values of the initial condition y and the parameter c fixed, and we'll just modify the start time of this ODE. For this case, the adjoint equation is quite simple. We don't even need to calculate the partial derivative of f with respect to anything. I want to spend some time to talk about the proof for this, because I think the proof I provide here is quite clever, and it uses perturbation theory, and it's different from the proof given in the paper. So here what we can do is we can convert this problem of calculating the change at the endpoint with respect to the start time to the problem of calculating the change at the endpoint with respect to change in initial condition. So what we can do is we perturb the initial time t0 by a very small value epsilon, and by doing so we end up at this point, which is y0 plus epsilon times f. And if we did not make this perturbation, if we began running this trajectory at t0 plus epsilon, then we would have started at y0. So you can think of these two equations as two equations where the start time is t0 plus epsilon, but the initial conditions for these two equations are different, and they differ by this value, which is epsilon times f. So essentially what we're doing here is we are perturbing the initial time, and by doing so we get different values at time t0 plus epsilon, and then we just assume that we began our trajectory from t0 plus epsilon, and taking the limit of epsilon we get this equation del L by del t0 equals minus a times f. In this case, f is equal to minus cy, which gives us this equation del L by del t0 is equal to c times y times a, and we can get the values of y from the forward trajectory, and we just need to run one backward trajectory, which gives us the value of a, which we can then plug in and perform gradient descent. As always, we have a target point, and then we run the forward trajectory. We end up a little bit far away from the target point, and then we run the backward adjoint equation. We get the point at the end time, which happens to be the start time for the forward trajectory, and we calculate the gradient. For the previous examples, I used a learning rate of 1, but in this case I use a much higher learning rate. The reason being the gradient is very small and the change is not going to be visible, so we'll be using a bigger learning rate. And once we perform the gradient descent step, you can see the value gets updated to minus 0.93, and the next iteration will start from this point. So let's perform the second iteration. This is the forward trajectory, this is the backward trajectory, and as you can see here, in just one iteration with a very high learning rate, we end up very close to the target point. We update the start point again and just perform a few more iterations. So that's the whole idea of neural ODEs. They allow you to calculate gradients with respect to input or parameters like starting time or initial condition, or parameters like C. In the actual implementation, you can make things a lot faster and more accurate by running one equation which calculates all these values at the same time, and to get the gradients you need to use VJPs, vector Jacobian products. Anyway, that covers the whole article and all three cases. That's it. Thank you.